Hello? Can you see my screen? Can you hear me? Okay. Good evening, everyone. My name is Hà Việt Thắng, and I'm from FPT University. And today, alongside with my co-author Châu Quốc Anh and Cường Trần, I will present our paper for the ICMLC 2026 conference held in Nanjing, China. And the title of our paper is Zero-Shot Shrimp Disease Detection with Vision Language Models, a comparison with a CNN baseline. So the core question that we're trying to answer is practical. Can general purpose vision language models detect shrimp diseases reliably in a zero-shot manner on real farm images? And how do they compare to a supervised CNN baseline trained on the same dataset? And we also measure the resource usages such as memory and inference time, because deployment constraints matter in aquaculture settings. And I believe our main message will be simple. In this dataset, the CNN is clearly stronger and more stable, while vision language models are prompt sensitive and less reliable. But still, they are useful for explanation in a hybrid pipeline. Here's an overview of our presentation. First, I will introduce the motivation and why shrimp disease detection matters, and then I will describe the dataset and the experimental setup. After that, I will introduce the vision language models, and then the shared prompting framework that we came up with. Next, I will focus on prompt sensitivity. This is a major theme because prompting strategy actually changes the VLM behavior strongly. Then I will present our CNN training and interpretation baseline, and follow that by a CNN performance evidence, including the 4-class confusion matrix. 4-class of what I will explain later. Then finally, I will present the binary screening results, the resource usage, and the discussion session, and then the hybrid pipeline for future work, and then the conclusion. So, what is shrimp agriculture and why is it important? Shrimp farming is an important source of protein and income. But farms are vulnerable to rapid disease outbreaks such as white spot syndrome virus or WSSV and black gill disease or BG. And in practice, detection often relies on manual visual inspections. And people often look for cues like white spots or darkened gills. The challenge is that this is slow and subjective. It depends on experience, and it becomes harder in real farm settings with low light, cluttered backgrounds, and multiple shrimp per image. And this motivates us to consider an automated screening tool that can flag suspicious images early using simple photo, uh, ideally taken from a smartphone. So the motivation is manual versus AI detection. Manual inspection, like we've been doing for hundreds of years, requires skilled labor. It is subjective and it is slow. And it can also be difficult in low light or cluttered backgrounds. An AI-based screening tool can be faster and more objective, and it can also work with smartphone images. But it also depends heavily on the model that we use. And for VLM's example, strong prompt. So the key framing here is the prompt is not a cosmetic detail, and for VLMs, the prompt is part of the decision system. That is why the paper In this paper, we like to evaluate both a supervised CNN baseline and out-of-the-box vision language models downloaded from the internet and testing them under the zero-shot strategy of prompting. I think it's important now to talk about the dataset that we're working on. The dataset that we used in this study is the shrimp disease BD dataset. It is a very popular open source dataset of images of healthy and diseased shrimps. It contains 761 images labeled into 4 classes: healthy shrimp and shrimp with black gills disease, white spot syndrome virus, and white spot syndrome virus plus black gills disease. The healthy class is the largest class with 424 images, and it takes up about 55.7% of the dataset. Black gills, on the other hand, has 111 images, and white spot syndrome virus has 109. And white spot syndrome plus black gills has 117, each around 14 to 15%. So the dataset is modest in size and moderately imbalanced. And this matters because models can drift towards predicting healthy unless disease cues are clearly captured. And the images are also realistic. They are not clean lab images where it is taken with clean backgrounds, and which makes the task harder. But this is meaningful because in real life deployment, images are rarely clean. Let's talk about the data characteristics and the splits of the dataset. Here, I want to highlight what the images look like and how the experiments are set up. Images are captured on real farms, the lighting varies, the backgrounds are cluttered, and there can be multiple shrimp per image. And for the CNN pipeline, images are resized to 224 by 224 and normalized using standard ImageNet style preprocessing. And for the supervised CNN baseline, we used a stratified split protocol for training and evaluation. For the out-of-the-box VLMs, we evaluate in a strictly zero-shot setting. No fine-tuning was done. And the VLM sees the image and the prompt and must answer directly what it sees. Let's talk more in detail about the models and the shared prompt. We test multiple modern VLMs under a shared screening prompt. The prompt defines healthy appearance and disease symptoms and instructs the model to output both a short description and a final label. The main evaluation focuses on binary screening, healthy versus diseased, because that is closer to a practical early warning tool. And in addition, we try to use VLMs on the forecast prediction task, but it turned out VLM performs very poorly in this task because they do not have prior training data related to images of healthy and diseased shrimp. Specifically, images of diseased shrimp of the 3 classes that are in this dataset. We also enforce a strict output format for the VLM models. If the textual model output cannot be parsed into the expected label, it is treated as incorrect. And this matters because one difficulty when dealing with vision language models is not only accuracy, it is also controllability and consistency. This is the 2 strategies that we used and how they differ. First is the aggressive strategy, which in the prompt we tell the models to err towards diseased when symptoms are mild. And This aims to maximize disease recall, but it can also create many false positives, as you can see in the confusion matrix we have here. The conservative strategy, on the other hand, requires stronger evidence, like clearly dark gills or clearly white spots. And this reduces false alarms, but it risks missing early or subtle disease. And the confusion matrices visually show the trade-off. One strategy floods predictions towards disease, while the other produces more balanced decision but misses more disease cases. So the takeaway is prompt strategy can significantly change the operational behavior of vision language model when dealing with screening shrimp diseases. Next, I will talk about in detail about the two prompting strategy. Here is the aggressive prompt text in full. Here I want to emphasize what is being controlled here. The prompt includes detailed definition of healthy shrimp and disease cues, and then it explicitly tells the model, if uncertain, choose disease. And that single policy instruction is enough to shift the model's decision boundary dramatically, even though the underlying model weights do not change. This is important for development because this is important for deployment and development because it shows that prompt engineering is not optional. It is equivalent to setting your screening threshold. And in the results, you see that aggressive prompting tends to increase disease recall, but can destroy healthy recall. As in the confusion matrix you see on the left here, the model basically predicts no healthy labels whatsoever, which is obviously very false. Next is the prompting strategy that is conservative. This slide is the full conservative prompt text, and the conservative prompt makes healthy the default and only switches to diseased if clear strong signs are present. It also includes more explicit guidance on what does not count as disease, like lighting artifacts, shadows, or background effects. So, the conservative prompt is attempting to reduce false alarms by tightening the evidence requirement. And this explains why conservative prompting tends to improve healthy recall and reduce false positives, but it can also miss disease cases when symptoms are subtle. Again, the key point here is the same model can behave very differently due to the policy language in the prompt. Okay, now let's switch to our CNN baseline for comparison. We use a transfer learning CNN approach with RexNet 150. And our approach was strongly inspired by a publicly published cargo notebook, which we cited in our paper. And the model is adapted into a 4-class classifier and trained with cross-entropy loss. In training, we use ADAM with learning rate scheduling and early stopping, which is typical for moderate-sized datasets, because the CNN is trained on labeled shrimp disease images. It can learn dataset-specific features directly rather than relying on general visual concepts like VLMs that were not fine-tuned. And this baseline is critical because it anchors what is achievable with supervision on this dataset. Okay, let's talk about the evaluation metrics that we use to, evaluate both the VLMs and the CNN baseline. We evaluate using accuracy, precision recall, and F1 score. The accuracy measures the overall correctness, The precision measures among the predicted disease cases, how many of them are truly diseased. Recall measures among truly diseased cases, how many we detect. And F1 combines precision and recall into one value. And for multi-class evaluation, macro averaging is useful because it treats each class equally. This is basic knowledge that we all learn in opening classes of artificial intelligence, but I like to repeat. And for screening, disease recall is especially important because missing disease is costly, more costly than missing healthy. But precision matters too because excessive false alarms make the system impractical. So the metrics here describe real deployment behavior and not just abstract performance. Okay, let's talk results now. Now we will look at the four-class setting for zero-shot VLMs. The main result is that zero-shot VLMs struggle with fine-grained shrimp disease categorization. They very often confuse black gills disease, white spot syndrome virus, and the combined class of both of those diseases. And they can also default to a majority like healthy, depending on our prompt. And this is not really surprising because these models are trained on broad internet data, not shrimp disease specific images. And the visual cues can be subtle. So in a four-way classifier of healthy, white spot syndrome disease, black gills disease, white spot syndrome disease, and black gills disease, zero-shotting VLMs that are not fine-tuned are absolutely not reliable in this data set. And this motivates us to focus more on binary screening, which we classify healthy and disease grim, because this is a way more realistic early warning goal. Okay, that was VLMs, and now we talk about the CNN baseline training and our GradCam plus visualization. Our GradCam style visualization shows where the CNN attends. The highlighted regions that you see here tend to align with biologically meaningful cues such as gills and shell areas that have visible lesions, which is consistent with disease symptoms. And that increases confidence that the CNN is learning relevant features instead of background shortcuts. Now, the key point for comparison is in this dataset, the CNN baseline is clearly stronger than vision language models for screening. And when the task is collapsed into healthy versus disease, we report very high accuracy, around 88 to 90% with the CNN baseline. It's one important caveat though. I will not claim that the CNN binary F1 here unless it is explicitly reported. So overall, the CNN baseline provides both better performance and more stable behavior than VLMs, even though VLMs are newer architecture. To further demonstrate the effectiveness of CNN over VLMs, here is the four-class confusion matrix that we produced on the test set. The confusion matrix shows that the CNN correctly separates healthy from diseased in most cases, and most errors happen between disease categories. So, in other words, the model may confuse white spot syndrome virus with white spot syndrome virus plus black gills disease. But it rarely confuses diseased shrimp as healthy. And this is exactly what you want from a screening perspective. Avoid missing disease, even if some disease types are mixed up. So this confusion matrix supports our claim that the CNN baseline that was supervised is more effective for this dataset. Now is the binary screening result. The binary classification simplifies the problem and generally improves performance compared to the four-class settings. I'm just elaborating what I've talked about here. For the vision language models, this also helped, but they are still unstable and underperform. Some are just too conservative and miss disease shrimp. Others become too aggressive and flag almost everything as disease. For the CNN baseline, on the other hand, the key reported result is that binary accuracy is around 88 to 90%, and the model shows strong disease detection behavior. So, our conclusion remains that the switching to binary classification helps, but it does not close the gap very significantly. A supervised CNN model is still the best primary screener in this dataset. Now is the really important part of resource usage, because in real life situation, you don't have access to state-of-the-art GPUs and computers. So what are the compute costs? We reported on CPU memory, GPU memory, and inference time per image across vision language models, and the differences are large. Some models require very large GPU memory and take many seconds per image, making them practically useless in the real-world setting because of their massive compute. Even lighter VLM models still require multiple gigabytes of GPU memory and seconds per image, which is much slower than a CNN classifier. So larger vision language models cost much more compute, but do not justify themselves here with better performance. And this supports our conclusion that vision language models are not the right tool now for binary screening under these constraints. As you can see here, more specifically, we like to talk a little bit about each of the model. The 5345 vision models is the worst performer here, with a total time over 9 hours to go through the 761 images. While the best return for investment, the best ROI is Quen 2 VL 2 billion parameters. And it also took a total of over 2 hours to go through all the 761 images, even though the CNN baseline went through the entire dataset in mere seconds using batch inference. Quen is the best return for investment, but small VLM is the lightest model, but still, it is slower and it is less accurate than the CNN baseline. Okay, so let's talk about the limitation of our studies, what we might miss and what we can improve. We obviously use VLM models that were downloaded from the internet out of the box. We did not do any fine-tuning or any further training. And therefore, the models were not trained on specific shrimp disease dataset. And shrimp disease cues are specialized and subtle. And prompt sensitivity is a real reliability risk because small changes can flip prediction. The strengths of vision language model can generate natural language explanations. They are flexible because you can inject definitions or context without retraining. So the correct interpretation is zero-shot VLMs are not reliable classifiers here, but they can be valuable as explanation assistants. That naturally leads to a hybrid approach. Speaking of which, this is our proposed hybrid system. The flow is an image goes to the CNN model first for fast screening, and if the CNN confidently predicts healthy, we stop. And if the CNN flags as diseased or uncertain cases, then we can call the VLM to produce commentary and explanation. And this gives compute savings because VLM inference is expensive and it runs only on a subset of images. It also gives interpretability because the VLM can describe what cues look normal, which is useful for farmer trust and decision support. So, the hybrid pipeline combines CNN reliability with VLM communication ability. Okay, so that's basically our proposed models, and therefore our future work and future path becomes clear. One direction is domain adaptation, such as fine-tuning the VLM models on shrimp disease images. This could improve stability and reduce prompt sensitivity. Another direction is instead of doing zero-shot prompting, we do few-shot prompting, where we include a small number of labeled examples in the prompt to guide decisions. We also need evaluation across farms, seasons, and imaging conditions to test generalization. Finally, uncertainty estimations and calibration would help to decide when to defer to humans or lab testing, which is critical for safe screening tools. So to conclude, zero-shotting vision language models struggle with shrimp disease detection in this dataset, especially for fine-grained classification. Binary screening improves result, but the VLMs still remain unstable and underperform compared to the supervised CNN baseline. The CNN achieves strong performance and much better reliability, making it the best primary screening model here. VLMs are most useful when used selectively for explanation and decision support. So, our direction for future studies is a hybrid model. CNN screening first, then the VLM explanation only for flat cases. This concludes our presentation. I'd like to thank the session chairs and our presentation listening. And thank you for your attention. If you have any questions, I'd be glad to answer. Thank you.
Just 1 minute.
Anyone join us? If no, we will take a photo. So look at the camera. 3, 2, 1. Smile. Wait a moment. I need to capture this. One more time. 3, 2, 1. Smile. Okay, thanks for your participation, and please keep in touch with us because there are some process about the paper publication need to conform with you. So please keep in touch with us. And that's all for the online special session. Hope to see you next year.